Okay, hi everyone, I'm Al. So I'm going to give you guys an introduction on pair distribution function. So since no one's really gone into more details, just a quick definition. Let's see. Oh, no, it doesn't want to work. Oh, there we go. Okay, so I'm just going to go over a brief history of how X-rays, of X-ray and X-ray diffraction, how we got to pair distribution function. Getting into a little detail about how X-rays scatter through matter, which will then build up to just a quick overview of Bragg's law and how powder diffraction is going to kind of fall apart and where PDFs need to step in. And we'll get into that real space, reciprocal space Fourier relationship, and finally go through the collection process, things to consider, and assuming we have time, some cool things we've been developing at Brockhouse about it. So we've seen a few parts of this touched on by Renfei as well as Joel. So we can go back to 1912, where William and Lawrence Bragg developed and formalized diffraction laws, and they won the Nobel Prize a couple years later. And then from there, a couple years after that, two groups started doing the first powder diffraction measurements. And about a decade after that was the formalization of the Fourier relationship between these X-ray scattering relationships and real space atom coordinations. So this was the groundwork that made the concepts of PDFs possible. And then just 3 years after that was when the very first pair distribution function measurement was done. And then at that point, the method pretty much sat on a shelf for a while until we get to the 80s when the first synchrotron experiment was done. This wasn't an easy feat. Measurements took a very long time, on the order of 12 hours to days to do properly, and that's after days of setup. Part of this is because energy-sensitive point detectors were being used to both cover high angles and only get the total scattering of interest. And so at that point, pair distribution functions started taking off and being used, but it was a very niche method. But around the 90s, there was a big boom in nanomaterials and governments starting to push funding into research of nanostructures and nanomaterials. And nanoparticles were a really good candidate for pair distribution function techniques. And the big revolution came in the early 2000s, 20 years ago, when PDF measurements started being taken with area detectors. And at that point, the big time problem that existed using these original methods went away because we can now collect a whole range of angles at the same time, much like how we do powder diffraction measurements with an area detector. And this now let us collect a PDF measurement on the order of seconds or minutes rather than hours and days. So if we look at how X-rays interact with matter, we need to first consider the fact that light is an electromagnetic wave and a photon. Because it's going to have an electric field and magnetic field, it's going to react and interact with charged particles. So we can consider the electron. In terms of PDFs, there's really two things we're going to be mindful of. One is elastic scattering, which is when that photon hits the electron. There's going to be a slight momentum transfer, so it's going to deflect a bit, but it's going to preserve its phase and wavelength. This is the scattering that we like. This is what lets us do X-ray diffraction and everything else. But the other thing that can happen is that X-ray goes, hits the electron, but it imparts some energy. So now that electron gets deflected a bit, it has some more kinetic energy, and that resultant photon scattering off is now redshifted. And so that's going to lose that phase and wavelength relationship, and if it shows up, it's useless data for us. So we really hate it, but we need to know that it exists. If we then expand out to an atom, our atom is going to consist of a nucleus and then a large electron cloud that's going to be defined by the orbitals that exist on it. We also now have to consider the fact that when X-rays scatter off of electrons, there's going to be a preference on the angle that it's going to want to scatter off of. So it's going to favor less momentum transfer, so it keeps that same angle, and that's where we're going to define this momentum transfer Q. That's going to be related to our scattering angle, 2 theta, as well as the wavelength of the photon. The other thing is that higher Z material, so the more electrons we have, the more opportunities there are for scattering. So we're going to see stronger scattering with higher Z elements or lower elements on the periodic table. And the way scattering falls off with angle or momentum transfer isn't just like a smooth Gaussian. You can probably, it might be hard to tell if you're far away, but these aren't very smooth curves. There's some like sort of ripples and ridges to it. And that's not me just trying to draw something freehand. This is actually related to the electron orbitals that exist in the material. So these things are very unique and actually dependent on effectively the scattering that would happen with just a single ion that's existing without any additional structure. So any sort of scattering pattern that we see is actually going to follow this trend as you go off in momentum transfer or scattering angle. Yep.
So this is pretty basic, but I just never really thought of it because in the nucleus there's always so many protons. But if you just had neutrons, would photons not interact with them at all?
Well, the photons are interacting with the electrons.
No, I know, but would they, if you only had neutrons, would photons just not interact at all because they're not charged? Or?
Yeah, photons won't be interacting with neutrons.
Okay. I just
never
thought of that. I never realized that. So.
But that's where neutron diffraction and neutron scattering comes in, which I think Graham's going to touch on a little bit. Hopefully. Oh. Well, you'll have some questions for Graham because Graham actually did a lot of neutron work. So once we get this, so now that we have that principle for that atom, if we imagine a crystal is going to be a whole mess of atoms arranged in this very periodic, repeating way. And we've already seen a bit of Bragg's law, but if those atoms start forming these nice, very infinite planes, we have cases where photons can come in and they can scatter off of these planes. And if these planes are spaced in the right way, we can get constructive interference or destructive interference, which starts giving us information and Bragg scattering that we can use in powder cases as a fingerprint for solving structures. One thing I also wanted to note is just this angle 2 theta. I think Renfei touched on it a little bit as well. 2 theta is always referring to the angle of the scattered photon relative to the incoming photon. And then theta just being half of 2 theta is just the angle of that scattered photon with the atomic plane. So us scientists, especially at beamlines, will always talk about 2 theta because it's our photons are always coming in at the exact same direction and we're usually moving everything else relative to that. So 2 theta is always going to be a very consistent reference point. And we've seen already how powerful Bragg diffraction can be, but in some cases it doesn't always work. Besides the obvious of something with no long range order, so liquids and amorphous materials, nanomaterial, as we start getting finite sizes, there's going to be peak broadening that occurs because we no longer can rely on the infinite plane of, or the nearly infinite plane of atoms that give us that nice constructive interference. So as that happens, we get more and more broadening due to that finite size limit. And as we get smaller and smaller, that also means that long range order starts diminishing away. And eventually we get to the point where things are so broad that traditional powder techniques are no longer going to be suitable for us to really glean anything about the structure. And we start getting this diffuse scattering. And if we just looked at powder diffraction, we kind of have to stop here, shrug and say, I guess we're done. But that's where pair distribution function techniques come in. So in the case of a pair distribution function technique, the experimental setup is very similar to that of just doing powder diffraction with an area detector. So we have our beam coming in, we have our sample over here, and then we have a big area detector pretty close by, so we can cover a very high angle space, which also means a fairly high space in Q or momentum transfer. And so that we get this nice little powder pattern over here. We can integrate that out. We can scale that to that atomic form factor. And then from there, we can do a little bit of extra math onto it, scale it by Q itself, where we can really emphasize some of those high Q features. And then using this f of Q, we can do a sine Fourier transform, which is through this integral. So we can kind of see the 1D sort of stages over here. So we start off with our powder pattern, and then we We divide it by the atomic form factor, giving us S of Q. We subtract 1, multiply it by Q. And we can see before where it looks like all these peaks kind of just disappear. You see a lot more peaks carrying out very far out. And then finally, when we do that integral, we're now in real space rather than reciprocal space or momentum space. And this is the PDF. We can also describe it in other ways. So we can actually rearrange it and turn it into something called the radial distribution function. And when we do that, this is the most, personally, I find the most intuitive way to talk about real space distributions because this is a direct, pure atom-atom histogram. So if we go along this, we go along in R, we're effectively looking at different spherical shells and seeing how many atoms show up within this thin spherical shell. So integrating over these peaks would actually tell us how many atoms are within that region. And that's our short range order. And as we go further out, we're getting further and further ordering that we can see. So this is possible. So that integral that happens seems like a very big step where things kind of magically happen. And I don't know how much people remember of doing Fourier relationships, but going from reciprocal space to real space is never intuitive. So I figured this would be a good chance to show some examples, and we can go into some of the nuances that we should keep in mind. So at its most simplest case, if we have a sine function, which is just a periodic lattice that goes off into infinity, and we take the sine Fourier transform of that, we're going to get a nice delta function. In more complicated terms, if we start considering the finite size, what we actually get is a convolution with a window function. So now we have to deal with the finite size as to how far out we go. And so what we're seeing here is something called a sinc function being convoluted with our delta function. So these ripples are something that you can often see around your peaks in a PDF. And this is a result of not integrating out far enough into your function. And we can see as we go further and further out, these little ripples start getting tighter and tighter. And because, of course, we're doing this infinitely tight, they'll never really go away. The other thing we can consider is as we start damping if we had a damp here, we can see we can start making those ripples go away. And eventually they start turning into a Gaussian as this function collapses more and more. So with that in mind, I'm going to make up a little RDF for us. So we can start off with something very simple and start working our way backwards to an F of Q. And so we can start seeing an idea of how little changes in real space can start affecting our sort of what we see in reciprocal space. So here again, I just want to start off with what an RDF kind of looks like. We have, in this case here, I just kind of have two peaks. And then as we go up, eventually we reach a point where random atom density is matching up with what we see. So at this point here where these lines converge, we have no more correlation in our materials. So we're going to start a little simpler and start off with one peak here. So again, here's that REF with just one peak. I'll convert it into a PDF. And what we'll see here is it's a little hard to tell just because this axis is a little stretched out. But there's this dip here that curves up and it eventually plateaus out at 0. The point where it plateaus out actually matches up with where those two lines meet, which is giving us sort of information about our particle size. And then when we kind of Fourier transform this, what we end up seeing is a damped sine wave relating to the fact that this is sort of a Gaussian with a decent width. There we go. If I add another peak into the mix now, in this case now we're going from 2 to 4, so the wavelengths of these two peaks are going to be half of the other. Again, now what we're seeing is this beating pattern starting to occur where one of these can contribute more or less, and we start seeing, and it's still damping away. And then finally, if we add a third into the mix, and I put this one specifically at 7, so that way there wouldn't be any nice overlap on this, we see the function starts looking even more complicated. So the main takeaway of this is that things can look really messy in reciprocal space, but through the magic of integrations and Fourier transforms, it can turn into something fairly simple. Yep.
What was your y-axis? Was it what would you say is your intensity?
Here. Yeah, this is just a scaled, normalized Fourier transform. So with that in mind, let's start working with a real material. So here, if we remember those steps that we took, we start off with, in this case, this is a nickel, and we're pretty tight in distance, so we can start seeing some rings, and they go out, and it seems like probably about here we can't really spot anything anymore. So we're gonna integrate that out into a 1D pattern, and just to make things easier, we're gonna pop things in a log scale. Yep.
Just to confirm, that's a powder sample.
Yes.
Right? Okay.
Yeah, we do the 1D integration of that pattern, and we can start seeing there's a little bit of signal here, but it gets things start getting very weak out to here. And this is where we can really see how that atomic form factor really scales with your pattern once you go into log scale. It's even though it's harder to tell at very high scattering, as it falls off it. Yep.
Can you? I don't entirely understand what the atomic. What did you call it?
Form factor.
Yeah. What is that?
So the atomic form factor is going to be the distribution or the preference of scattering off of a single atom of that material. So this would be for how an uncorrelated, completely uncorrelated, not even amorphous, like beyond amorphous, no ordering whatsoever. No ordering whatsoever of nickel or whatever material you would be using. Yep. Yeah.
If you want to know what mathematically the atomic form factor is, this is the Fourier transform of the electron density around an atom.
Oh, okay. Yeah. But I mean, I think practically, right, they use like really low density gases originally for getting the experimental form factors, if I recall correctly.
So would it be like the average of everything, and that's why when you get really far out to where you don't really have any signal anymore, it's just kind of.
No, it would be like Boss said, which is that it would be what it is for a single atom.
Okay.
But one of the things that at least scientists used to do back in the day, or at least one of the quick and dirty things that you could do, is you because it always is going to follow that form, you can usually people used to get away with just kind of freeballing it because it always does have to follow that form, and you can usually get, if you know nothing about your sample, you can get surprisingly far by just eyeballing what that form factor should be by eye.
Okay.
Yep.
I could add a different sort of explanation that maybe there. So, like when you have a collection of electrons in an atom, right? Then you're having scattering off that atom, since it has a size, and you're going to get scattered from different parts of the atom, and therefore you get partial destructive interference. Because the atom isn't like a tiny little point compared to the wavelength. So, like if it scatters off like one part of the atom or another part of the atom, that scattering isn't completely in phase, so it's partly destructive. And how destructive it is depends a lot on the angle of the scattering. So if you're coming in at a really low angle and out, it's almost completely obstructive. Where if you come in at high angles, then it becomes almost completely destructive. And so the scattering from the collection of electrons that makes up an atom is very dependent on the angle for how much of it is like destructive interference from within an atom. And so that makes that's one of the reasons why X-ray diffraction patterns fall off at high angles, because the individual atom contribution. So the form factor is just showing how much an individual atom scatters at a particular angle. So at a very low angle, it's just the number of electrons, basically at zero angle, and then at high angle it drops off very quickly.
So a single atom is basically has each atom with increasing z has its own like fingerprint intensity per angle.
Yeah.
Essentially. Okay.
So ones with more electrons will have more intensity, and then you can see ones like, maybe if I was to go back a few slides, you can see like where there's I think it has different ions, like the calcium 2+ and the chlorine minus, right? They're isoelectronic. So like at zero, they're the same because they're the same number of electrons, but then they differ slightly because the calcium one The electrons are more compact, but the clay ones are more diffuse. So the more compact it is, then the less destructive interference you get. So even though they're isoelectronic, they don't scatter exactly the same at the same angle, because the more compact atom has less internal destructive interference.
Okay. That helps. Thank you.
Yeah, that's sort of a word description of what a Fourier transform is.
Yeah. Mathematically more intuitive. That's how I think of it.
So yeah, we take that, so we have that atomic form factor, and we can now normalize to it. And so that's all that's really happened here. So we're still seeing something very similar to that raw integrated scattering pattern that we have, except now rather than it just falling off, it kind of normalizes out towards 1. And then this is where we're going to do that change from this being S of Q to that term F of Q, which is also going to show up in programs like GSAS when you try to do create PDFs through there. So again, we just have that form up there. We're just subtracting out that normalization of 1 and then scaling the whole thing by Q. And we can see once again here where this signal here is incredibly weak and hard to resolve. Once we multiply it by Q, it still looks very strong even out when we're out at our max angle. There's still signal there. So that almost tells us that we haven't fully captured all the signal that we could for our PDF. And then now that we have this, we do that integral again. And one thing that we'll notice is that there's this fall off in the pattern that's linear. And this actually has information. It's going to follow this trend of being related to R as well as the number density of the material. So you can start getting density information from your material just from that downward slope. And using that, we can then convert to get a radial distribution function where we can see how it follows the trend for just a completely uncorrelated material. And at that point, those are the steps you need to just construct PDFs and RDFs. In terms of what we can start doing with that information, there's a lot of things, and I think Graham's probably going to go into more details, especially in the modeling aspect. But this becomes very useful for nanoparticles, where we can start characterizing particle size as well as structure. We can start doing actual modeling with it, similar to how we would do structure solutions, or analogous to doing structure solutions with powder. And I think Graham's going to go into more detail with that. We're actually going to do some tutorials with that. And we can even use it as a comparative tool to find evidence of atom-atom interactions. So this was a case of single atom catalysts where we wanted to see if nickel was actually being dispersed individually within our catalyst, or if there was just nickel aggregating amongst itself. So we can compare the PDF of just pure nickel and seeing what those nickel-nickel interactions are, and compare it to our catalyst mixed with nickel. And we can see whether there's the presence of certain peaks or not. So while this all may sound simple, or especially for anyone who's done powder diffraction measurements before, there's a lot more things that we need to consider and be mindful of than when we're doing powder diffraction with an area detector. The biggest thing is going to be dealing with the fact that because we're doing a Fourier transform, the resolution of Q that we get with our detector, as well as how far out we go in Q or our momentum transfer, starts having a big hold on how our PDF is going to end up looking like. Sample quality is also going to become important. Much like powder, we really need something fairly uniform and consistent in range, so we don't want things that are too grainy or spotty, because that's going to mess with our averaging, as well as things like preferred orientation, which can start messing with our ability to get something that's spherically symmetric. And then the other thing that we really have to be careful of is scattering of anything that's not our sample or of things of interest. And that's going to include things like detector noise. Because we're doing that transfer of all that information, we need to make sure we remove anything that's not important. So in terms of going out far out into Q, we kind of saw a little bit of these things. an example here is just even with an amorphous material. If I adjust how far out into Q we go for something amorphous, even when we have broad peaks, we can start over broadening nearest neighbor interactions just because we're not getting those that damping sign function to go far enough out. So we get artificial broadening. We can kind of see this over here when we look at if we just vary sample detector distance, where we go out certain distances, but we'll start seeing that when we go further in Q, we get sharper nearest neighbor peaks. But as we go further out to larger radii, now the effects of our Q resolution being dampened because we have finite pixels in our detector means that our long range ordering is being compromised. And we can see this a little better here in just this little zoom in, particularly here in the orange and the black here at these two different extremes. Sometimes we also have to pay attention to acquisition time. And when your sample's good, you can get away with a lot less. But as you count shorter, you can get a lot more noise here, especially out at high Q. And that can create some noise that you have to be mindful of. The other thing, circling back to one of the early slides, is Compton scattering. So because if you remember back in the 80s, we were using energy sensitive detectors to collect our data. And one of the reasonings for that was that we wanted to make sure we were just getting our actual scattering and not Compton scattering or fluorescence from our sample. And the tricky thing about Compton scattering is that we get more and more of it as we go to higher angles, where we can start imparting energy, and that energy of that scattering photon actually starts dropping as we go to higher angles. And if you don't have an energy sensitive detector, it can start polluting your sample. This is a bigger problem at lower lower Z materials as you're working at higher energies. But the nice thing is that usually with a lot of software, the effects of Compton scattering are usually fairly well understood. And we can, as long as we know the materials, we can usually model and artificially predict and remove it. And then the other big thing is non-sample scattering. So if we remember that first nickel example I showed, this now is just an empty capillary that I put in. And I adjusted the gain and color correction a fair bit, just so we can see all the crap that exists within it. So I guess one of the few things we see is we see some bright spots here that starts dimming away. We see these weird tails that's coming from scattering, hitting the beam stop. It's probably hard to tell on here because the contrast isn't great on a projector, but there's actually very tiny diffuse rings here that's from the Kapton holder itself. And then there's also this little weird shadow here, which is actually air scattering being shadowed by our sample holder. So while this is very little, it can all contribute into it. The nice thing is that the solution to this is we just need to collect this data and have it in our back pocket so we can subtract it from our data. If you have very dense samples that are very attenuating, you might want to have more subtractive samples because you might have to play with scaling of how things need to be corrected since your sample is also going to be blocking some air scattering. But the very important thing is that we need to get background images of our sample, of our empty capillaries or empty samples of air, and even with no signal sometimes, depending on your detector. Yep.
Just a quick question. To deal with the Compton scattering,
Yeah.
I guess since you're using multiple wavelengths, you'd have to do it one wavelength at a time. But could you just have a filter that removes all the lower wavelengths or lower energies? Therefore, you're only accounting for the perfectly reflected.
So experimentally, you can do things like that. The big trade-off there is time.
Yeah, because you have to take one for every single wavelength.
And often being able to filter out energies like that without compromising your signal makes things a lot more complicated. There's been some work where on the side, there's been an energy sensitive detector to scan things to look at the ratio. But these things are often it's weak enough that you can get away with correcting by correcting it through simulation.
Okay.
It's not as detrimental, which is why area detectors have taken off, but it's important enough that I felt that it's worth mentioning.
Okay.
So I'm running a little low on time, so I'm going to skim through some things here. So Brockhouse, and particularly the high energy Wiggler beamline, is the place here to be doing PDFs. Part of the reason is that we have the energy capabilities to go high enough to do it as well. And then we also have the options of being able to put in a lot of different sample environments and do in situ and in operando measurements. And for you guys hoping to do PDF measurements, I would say I'd break down a few tips or things to keep in mind. The first is going to be, before you do your experiment, think about what you're hoping to understand about your sample. So are you looking at, do you want to figure out what's happening in terms of short range order, medium range order? Are you trying to see some comparative changes over time? Or are you hoping to actually model and solve the structure quantitatively? All of these things are probably going to define what sort of compromises that we can make in terms of doing a measurement. So in the case of modeling, we're going to want to do something that's going to be the most quantitatively consistent, and that might come at the expense of time. Whereas comparative changes, there we can focus on the region of interest that you're in, and we can really do churn out fast accumulation since you're just looking at relative changes. In terms of short range ordering, if you're really focused on short range ordering, we can get away with, we would want really high Q. Whereas with medium range ordering, we'd probably want to pull back to make sure that you get that good Q resolution to be able to resolve out medium range order. The other thing, this one is usually harder to know offhand, but if you do, it's great, is that if there's very low Q or low angle scattering in your materials. As we bring things tight and things get condensed, it's very possible for complicated structures to have peaks that just get covered by beam stops as your region, as your area of interest gets tighter and tighter. Or if you have something very high, either way, it's good for us to know to plan your experiment accordingly. And then in terms of things to be aware of, these are things that you probably don't need to know prior to an experiment, but these are good questions to ask your scientist, and they should be able to tell you, all these things and ease your mind about them. So choosing your energy in terms of what you're hoping to get in terms of Q as well as flux, knowing a bit, asking about the area detector being used, so knowing if there's any quirks about it, how big the pixels are. So quirks would be things like, is there afterglow on it? So if you have a really bright signal, does that signal kind of persist for a while? Is there dark current? Is the gain on the detector kind of weird? So do pixels respond consistently? Where does it saturate at? All these things can be mistakes that can be made that can ruin data. And finally, collect more background and subtractive images than you think you need. There's usually no harm in collecting more if you don't need it, but there have been many times where people have forgotten to collect something, and going back and doing it once the setup's changed is nearly impossible. And at that point, all your data you have before can potentially just be useless if you don't have the right subtractions. So always make sure you get a lot of backgrounds for things. I think I'm very tight on time, but I'll just quickly skim over some of the cool, okay. We're gonna skim over this fast. So one thing that we're doing in Brockhouse, and I think Bob even touched on this a bit, is tilting the detector to try to get higher resolution PDFs. And so the advantage is that we can cover higher angle space without bringing the detector too close, so we can preserve Q resolution. And we can actually see here, it actually has this double compound effect, which is we greatly improve our Q resolution at low angles, which is where we usually have the brightest, sharpest peaks in crystalline materials. And then we have our worst Q resolution at high angles, where our signal's really weak and we actually need all the help we can get. So it also, in terms of, we both improve our signal as well as give ourselves effectively better dynamic range. Unfortunately, as you go into these extreme detector conditions, alignment becomes very tricky, very easy to be slightly off without realizing that can have detrimental effects. You don't get full ring averaging, which means your statistics can drop a little bit. And also now, as you go much higher out into Q, detector corrections that you need to do become a lot more complicated. And so it takes a lot more elbow grease in programming to work around it. But the good news is that a lot of this has been starting to be figured out. And it's going to be hopefully a method available soon next year, if everything goes well. But the differences that we can get by just being able to go out further in the queue gives us much stronger signals with much less much less of those termination ripples, as we're giving our sample more chance to actually die out naturally. And we can start resolving and being able to model nanomaterials and stuff very carefully. So just to sum up, PDFs are really awesome. They're really useful. They cover everything. You can work with crystalline, non-crystalline, nano, everything in between. And with synchrotrons, we can go really fast, so we can get things that are time sensitive. We can get things that are quantitative, and we can really get that local structure information. GSAS2 is very great software to work with, and I think we're going to have some tutorials on that tomorrow, led by Graham. But one thing I would recommend is try to play around with it on your own, with your own code. The math is, I laid out some of the math already. It's something you can try along with GSAS. I would always use GSAS for actual data, but to play around with, you'll get a finer understanding of what's happening by just trying to do it yourself rather than clicking buttons for all the ease that GSAS offers. So I just want to thank our Brockhouse team. I think we've seen most people. We're going to see Narayan later today, and I think Feiju tomorrow. And Stefan Kitcho is our Beam team leader here at Brockhouse. And here's a few resources of things that I would say were worth reading or checking out. And with that, I'll take any remaining questions we have. Yeah.
If somebody else
wants to
ask your question first.
So when I start, since you are doing the Fourier transform interaction pattern, so probably there should be a minimum distance between detector and sample, right? That if sample is very close to detector, closer than a minimum threshold, then we shouldn't be able to take the Fourier transform reliably because we are in the Fresnel diffraction region. But the distance should be enough far, so we are in front of them. Is this correct?
Okay, so in terms of distance, we're usually talking like a small distance that we do in PDF, which is usually on the order of like 100 millimeters. So we're very far out from like that near field diffraction area. One of the problems I didn't touch on is as you get closer and closer, usually the problems that start emerging is the effective parallax and absorption as you get really close to your detector, because you're starting to like come in at really sharp angles on these, and so at high angles, those corrections start getting a little more complicated. You start knowing a little more about your detector in terms of like layers that are there and the attenuation that can happen on your detector based on materials. And then the other thing is as you get tighter and you need to block your beam, you start losing a lot more low Q information, which is going to have information on longer range ordering. Depending on what you're looking at, that may not be important, but it is important. I think Adam's going to talk about the importance of low Q stuff tomorrow. Does that answer things? Yeah.
So just really quick, after you do this whole transformation, you do the integration and you do the Fourier transform, and you had that graph on the bottom.
Yeah.
What was the meaning of the location versus the intensity? Or like, what's the meaning of the location of those peaks or the intensity of those peaks? What are we getting from that?
Let's pull up. A nice. Yeah. So this here is containing. This is just a scaled and slightly deformed version of an atom-atom histogram. So while not direct, this is telling you information that as you go further out, the probability and the density of atoms that exist. If you imagine an atom at the origin, we're looking at distributions of atoms as you go further out in R. So very sharp high peaks are telling us there are very tightly distributed atoms at a certain distance away. And as you go further away and you see nothing, there's nothing there. See another sharp peak, there's more atoms there. A broad peak is telling us atoms are kind of broadly distributed away. So,
and this is in angular space.
This is in real space. This is R.
This is in real space.
Yeah, this is R. Yeah, so that's the power of that Fourier transform.
Yeah.
This is a very nice figure that shows that I can show it structure and you calculate that. So the first pair, the closest pair of atoms is at this distance. That's the first
Here, let's do it this way.
Then the second closest is here at this distance.
And this is for a crystal structure.
Any structure.
Oh, any structure.
Yeah, so even amorphous, there could be short range ordering, right? So if you imagine any compound, right, there's still some chemistry there. So you'll actually see atom-atom histograms. So let's see, this is gonna look a little messy, but imagine this is our origin atom. So we have, let's just say we'll pretend this is a nice little circle. We'll call that 2 angstroms. That means in this RDF, there's gonna be this sharp peak at 2, and the area of this peak is going to be 4. Is going to correspond to 4 atoms being there.
I see.
And then if we go further out, we're going to start looking at the interactions of maybe only some of these get caught. So we'll see another one, and then there might be like a slightly weaker one here catching that in a little other shell.
And so the origin is just where the center of your X-ray spot is.
It's an arbitrary center for a given atom, right? So this is averaged over every atom that your X-ray is hitting.
I see, okay.
So in the case of if you have like different elements, you can imagine it's almost an amalgamation of all those at the center and the other positions.
So
Yep.
this is somewhat similar to like an X-HAPS technique, but it's using diffraction instead of like X-ray absorption.
Yeah. Yeah, the difference here is rather than using, I think with X-HAPS, you're looking at like the like shifts that show fingerprints for bond lengths. This is a direct sort of Fourier transform of like that signal that you get that gives you that R distance.
Just to verify that, like the X-axis will give you distribution distances around one particular atom type.
Yeah, that's really
to the
There's one
PDF
slide
all the atom pairs.
the next slide here.
So X-axis is like partial PDF for just like one type of atom, looking at all the other types of atoms. The X-axis also it dies off very quickly. It'll tell you something about the nearest neighbors and maybe a little bit about like the second or third nearest neighbors, but nothing about like the key
Yeah.
This is what he wants to know. And the one with the coins there. So if you want to.
Okay, let's see. Beatrice has some figures here.
Didactic slides here that show what those peaks mean.
Oh.
There. So let me show you first I'm going to show the very basic one. So you see this one. I really like this one here. So this show you what is PDF. Let me see. It's per distribution function. So let's take the example on the left. The atoms are the coins now, right? And that's the structure. How many coins can you find at the closest distance, which is 2R? That seems like a 9. So you have a peak of height 9 at that distance, at 2R. Now that's the first neighbor. The second neighbor is a bit farther away at 3 something radius, right? And you can find 3. You're going to have another peak there of height 3, and so on, and you go. So that's the third distribution function in the histogram, the distribution of your neighbors per distances. I'm going a bit deeper on that. Let me page down. Sorry. There's another one here. I'm gonna get there. This one here. That's another slide I got from that paper there. I really like. So, yes.
Yeah, I see.
Peak position goes with atomic distance between atom pairs of atoms. The peak area is the coordination, how many you have. The more, the higher the peak, the larger the area. The peak width, are those neighbors exactly at the same distance or a bit messy? And your peak gets broader or narrower. And the particle size, the signal is going to die at some point. When your particle ends, say you have 20 nanometer gold particles, you will not see any peak beyond 20 because they are in neighbors farther than you. So your signal dies. And you can easily get nanoparticle size from this technique, like that.
Yeah.
So yeah, I found that really intuitive.
Yeah, that makes a lot of sense.
Direct space, no confusion with reciprocal space or something like that. And it's so intuitive. So, I mean, very powerful.
I might have one more quick note, because I'm not sure if it was mentioned. So the intensity of the peak depends on how many neighbors there are at that distance. It also depends on how strongly those neighbors scatter X-rays. So like heavier elements will create stronger peaks. It depends on the scattering power of both the elements that making up the pair.
But that's why we normalize it with respect.
No, because you can still have different elements in there. So
that's right.
If you do a nickel oxide, your nickel peak is going to be the strongest probably because nickels are scattering a lot more strongly than the oxygen.
Yes.
Yep.
Your diffraction pattern reciprocal space starts from 0, which we can say detector center, towards a certain amount of reciprocal distance, that is the boundary of detector.
Yeah.
So when you take the Fourier transform of this diffraction pattern, on the two boundaries, if it doesn't approach to 0, it will cause some artificial peaks in your diffraction. Do you do any extrapolation to 0 on two boundaries?
So you can. It's something I don't recommend because so these ripples here are the evidence of that finite boundary. You can do things like add an artificial damp function to smooth it out so it goes to 0. But what you're doing is you're adding an artificial damp. So if you remember back as I played around with that damp, that peak got broader and broader. That's what you're doing to your real data is you're convoluting it to making it broader for the purposes of getting rid of termination ripples. So you're basically killing some of your results for removing artifacts.
More questions? I will be hanging around today and tomorrow.
Yep.
If you come with a late question, you can always
Yeah, you can stop.